All right, so we've talked about exponential functions and logarithmic functions and the relationship being inverses and how to solve equations no matter which one you have and how to use either one of those functions to solve another equation. So we do all this work so we can start applying it to real life situations. Today we're going to talk about double time as our major concept, and that's part of continuous growth. And then we will develop the two different ways to write the same formula, either using a base of 2 or using the PERT formula. For those of you who learned it in the previous units or previous sections and want to stay with it, you can do that. We'll specifically talk about how to get the rate of growth, the growth rate, by using the double time, and then we'll extend it on to triple time or quadruple time or 100 times bigger. If we just know the proportion of how much it gets bigger, we can figure out the rate if it's something that grows continuously. So let's talk about a certain bacteria. Initially, you start off with 25. So in the table, we'll see that we have times 0, we have 25. Okay, and it observes the double every 5 hours. So let's just make this table where it's going to double 4 times. So if we double the first time, we're going to have 50 here. And then doubles to 100, then doubles to 200, then doubles to 400. Okay, so that's the first thing we're going to go put in our table is the doubling. Now it says it doubles, if we go back to the reading, it doubles every 5 hours. So the time to go from 25 to 50 takes 5 hours. So after you start with 25, for it to double twice, it's now going to be 10 hours. So to double 3 times, it's going to be 15 hours. To double 4 times, it's going to take 20 hours. Okay. So the next thing we're going to be asked to do is find a model for this. So that's the N of t. We're going to use function notation, the population, the number of the population as a function of time. We're going to write that as a model here. So in order to write that model, what I'm going to do is I'm going to write some work off the table and try to relate the t value we have into these numbers here. Okay, so if we think about it, this one right here is just 25 to start with. I'm going to eventually try to manipulate it so they look all the same, except for I'm going to have one thing changing, and we'll see the numbers 0, 5, 10, 15, 20 changing. And that will tell us where to put the t in this. Okay, so to go from 25 to 50, all I did was times by 2. And then go to 100, I times by 2 again. And then we want to 200, we times by 2 again. And then we times by 2 one more time to get to 400. Okay, so I'm going to put the 1 there for timesing by 2 the 1 time. So this means I times by 2 0 times. So I can see that we have 0, 1, 2, 3, 4 as the only thing that's changing. Okay, so if I just put those over here, what I want to do is I want to turn the 0, 1, 2, 3, 4 into something that I can actually go and use over here. Okay, so let's rewrite these. I want to turn these 0, 1, 2, 3, 4 into 0, 5, 10, 15, 20. So what do I have to do to 0 to get 0? Do the same thing to 5 to get 1. Do the same thing to 10 to get 2. You do the same thing to 15 to get 3. You do the same thing to 20, and you'll get 4. To me, that sounds like you're dividing all these numbers by 5. So we have 25 times 2 to the 0 divided by 5. 25 times 2 to 5 divided by 5. 25 times 2 to 10 divided by 5. 25 times 2 to the 15 divided by 5. And finally, 25 times 2 to the 20 divided by 5. So the numbers that I see changing right here, the 0, this 5, this 10, 15 right here, and the 20 are the values of t. So that means in my equation, I really have 25 times 2 to the t over 5. All right, so now we're ready for part C. Part C says, how many bacteria are in the colony after 15 hours? So you could take this and just put the function in and put 15 in for, type your function in and put 15 in for the table over here. Or as we can see on our table, we've already done this value and it's 200. Using the calculator like this can kind of verify that I actually was on the right track to start with. So there are 200 bacteria at this point in time. All right, last part. After how many hours will the bacteria count reach 100,000? So what we're going to do is we're going to put this in for the y value, the n of t, into our equation that we had just came up with in part B. So we have 100,000, and that equals 25 times 2 to the t divided by 5. So I'm going to divide each side by 25 first. Order of operations backwards. And now we get, see, 25 goes on 104 times, so it's 4,000 equals 2 to the t divided by 5. Now, if we want to, we could take this and use the definition of exponentials and logs like we're solving equations and do log base 2 of 4,000 equals the exponent t over 5. We could also take the last method that we talked about, the sledgehammer method, where we could take the natural log of each side, take any log of any base of each side. And I'm going to go ahead and do this for something we're going to see pop up later on. So let me take the natural log of each side, and then I could take this power out in front. So I have the log of 4,000 equals t over 5 times the natural log of 2. I want to get t by itself, so I'm going to times by 5. And I'm going to divide by the natural log of 2. Again, if you wanted to, you could have used the definition log base 2 of 4,000 equals t over 5. And you could have times each side by 5. And then you could have used the change of base formula. All right, so let me go type this in my calculator. I don't care if you want to use the change of base. If you don't have that special log button, you can use this one. Or if you have that special button, you can use this one. It doesn't matter which one, you should get the same answer. So 5 natural log of 4,000 divided by the natural log of 2. So the time that would take would be 59. Let's go 3 decimal places. And we can round or truncate, I don't care. 8,289. So if you want to round, that's fine. And the label for time in this problem was hours. All right. Note there's this 5 over natural log of 2 that we're going to see. We're going to see something that involves the 5 and the natural log of 2. The time it takes to double and the natural log of 2 involved in the next few slides. Okay. All right. So if you want to talk about something doubling, you can use your base as 2. If you want to talk about tripling, you use the base of 3. Quadrupling, base of 4. If you know how much time it takes for it to get 100 times bigger, base of 100. So you can set up a whole family of parent functions using this concept. Now in this problem, n sub 0 is the initial amount. So n sub 0 is the amount that you have at time 0. So an ordered pair, it would be this value, whatever number here. And the t in this problem is your variable t. And a is the time it takes to double or triple or whatever it's going to be. So if you're using a base of 2, a is the amount of time it takes to double. That's the doubling time. Okay. Again, if it's a triple problem, it'd be the time it takes to triple. You would use a base of 3. All right. Now, there is a way so you don't have to do a whole infinite family of parent functions where you can get it down to just one function every single time. Some people like to use the base of 2, and if that makes more sense to you, go ahead and use it. But this next one, it doesn't matter what we're doing, whether it's growth, decay, double, half-life, triple time, we can work with this concept over and over again. So we're going to use the ratios of A to P. So what we're going to do in this problem is we're going to start with A equals PE to the RT. So something that's growing in a continuous fashion. Okay? So what would I do to start getting the rate and the time, whatever I'm looking for, whether it's the rate or the time by itself? Well, I divide by P first. And then how would I get rid of the E? Well, to change that, I would use the definition of a logarithm. So log base E of your number, which would be A over P, equals the exponent RT. So if you think about what this A over P really means, A over P is the ratio of what you have versus what you started with. So if A over P equals 2, we would say it doubles. If it equals 3, we say it triples. So if I know if it doubles or triples or whatever, it's just giving me this number right here. So if I have this, if I know how much time it takes to double, I can find the rate. If I know the rate, then I can find the double. So that's what we're trying to say in the next 2 lines here. Now, we've had this concept many, many times in this course in a lot of math classes, and especially a lot of science classes. We have something that has a rate, a nice, easy little, like, it looks like a linear equation here, okay, where you have this little, like, rate times time equals the natural log of your ratio, okay, like distance equals rate times time, or like work equals rate times time. And in some of those classes, you may have seen this little magical triangle where you put the distance in the top or the work in the top. Well, what's going in the top is the natural log of that ratio. So if it's double, you put 2, triple, you put 3. And then you put rate times time in the bottom. So if you cover up one of these things that you don't know, then you can find out how to get it by looking at what's left. So if I take and cover up the natural log of the rate times, or the natural log of the ratio, it'd be rate times time. But what's really going to happen in these problems is maybe I want to know how long it takes to find, or how long it takes to double. So if I'm looking for that double time, I would take the natural log of 2 and I'd put it over the rate it's growing at. If I know how long it takes to double, but I'm trying to figure out its growth rate, then I take the natural log of 2 and I divide by the time it takes to double. So that capital T is a very specific time. That was the A we saw in the previous slide. Okay. So you might want to have this handy and study so you know how to use this when it comes to test problems. Just a warning, those of you that might be trying to think, oh, I can just use Photomath to do these problems. It won't help you. So to do these type of problems here, you're going to have to actually understand the concepts, because Photomath does not break down word problems for you. You really want to make sure you have this page here with how to find the rate or the time, whatever you're looking for, ready to go. Okay. All right, so let's take the exact same problem we started with, the same bacteria, and with the same initial amount, doubling 5 hours. So rather than make a table this time so I can try to figure out how to get the formula using a base of 2, I know what my formula is going to be. I know my formula is going to be A equals PE to the RT. I just need to find P, the initial amount, which was given to me, and I need to figure out my growth rate. So I need to find out R. So to do part A, I know in this problem, it doubles, telling me my ratio is 2. And I'm looking for the rate, so that's R, and the time it takes to double is 5. So this is my double time. So that's that capital T I had in the previous slide. You can write dt for double time. So if I want to go find my rate, it's the natural log of 2 divided by 5. Okay. So I said earlier when we saw it, we had something like 5 over the natural log of 2. We're going to see where that comes into play here in a little bit. We're going to talk about this last problem, part D. So there's my rate. Now, for some of us, we want to look at it and say, hey, it's a percentage. So if we want to do that, we can do natural log of 2 divided by 5. And it gives us this number here. But if I times it by 100, that gives me the percent. So this growth rate is 13.862%. And this is an hourly growth rate because we use hours to figure out our problem. Some people would just write it as 0.13862. So if you do the percent symbol, you got to times it by 100. If you don't use the percent symbol like we do in our calculations, you got to take your percent and divide it by 100. Now, I'm going to go ahead and store this rate that I had before. Let me go back to our natural log of 2 divided by 5. I'm going to store that. I'm just going to call it A. So that way, if I don't want to retype natural log of 2 divided by 5 over and over and over my calculator, if I just type in A, I get that number as I need to. All right, so part A is done. Part B, just the same thing we did before, write an exponential growth model. Rather than trying to figure out the pattern like we did before by using the table, I'm just going straight to A equals PERT. If you want to call it N of T like the book does, that is fine. I don't really care. So we're going to take our initial amount, which is 25, E, and our growth rate, which is natural log of 2 over 5, and we're going to times that by T. Okay. If you don't want to use the parentheses there at the end, that's fine too. Okay, as long as it's a big power here. All right. So there is our formula. Okay. We'll show on the next slide that this is actually the exact same equation that we came up when we did this problem the first time. All right, part C. After how many bacteria in the colony after 15 hours? Well, it's the same problem we had before. I believe it was 200. We should be coming up with that same answer. Let's just go plug this in. So I'm just going to put the 15 in for T. Now you can go grab your calculator. That's perfectly fine. So I'm going to put 25. You've got to use the base. A lot of people forget the E for some reason. You have to. That's a number. Without that, it doesn't make any sense. Okay? You're trying to say it's getting 25 times bigger if you're going to do that. It's not what we're talking about. We're saying it's doubling or it's growing continuously. Your rate, which I stored in as A, times 15. And there we go. 200. So there's 200 bacteria. By the way, if for some reason you're going to a class in the future and they say, hey, you don't get a calculator, you could have evaluated this by hand. 15 divided by 5 is 3. And then you could take that 3 and put it as a power to the 2. And those would divide out. And now you have 25 times 2 cubed, or 25 times 8. And think about it, 8 quarters, $2, 200 cents. That's the answer we came up with. I highly suggest, though, if you have a calculator, just use it. Okay? All right. So B and C are done. Now let's do part E. All right. So the next thing says, after how many hours will the bacteria count reach 100,000? So I could put 100,000 in for my A. That'd be 25 e to the natural log of 2 over 5t. And then I can start solving. So if I divide by 25, I get 4,000. Now, honestly, if I was taking my test, I'd be almost done with my answer by now, because that's a ratio it's growing at. And I want to figure out the time it takes to reach that ratio. So all I have to do is take the natural log of that ratio and divide by the rate. Well, this is why we're doing that. We convert this to a logarithm, it'd be log base e, or the natural log, of our ratio, 4,000 times bigger, equals our rate, which is natural log of 2, over 5 times our time that we're looking for. So if I divide by my rate, my time now becomes the natural log of the ratio divided by our rate. And when you divide by a fraction, you can go ahead and multiply reciprocal. So if I realized it went from 25 to 100,000, I could have just put that quotient right here and immediately divided by the rate and been done with this. And this would be in hours again, because that's the unit of measurement we were using for our time. So it should be the same amount of time that we had before. Okay, we've already done this calculation once before. I'm just going to go highlight it up here. So that is 59.8289 hours. If you go more decimal places than 3, I'm happy with that. So some people like this method better because it's only one formula they have to worry about memorizing for the growth rate, or the growth formula. It's just continuous growth. They already know it from the previous unit. So the real thing we're trying to do is find out what's that rate. Natural log of the ratio you know divided by the time it takes that ratio to get to that ratio. A lot of people go straight here without any work to get their rate. Okay, so here's the PERT formula. We're just calling A N of T, we're calling P N sub 0, like they would in a science class. If that bugs you, stay with A equals PERT. Okay, so let's show that the two formulas we came up with are the same. Well, we have this T over 5 being multiplied to a logarithm. If something's being multiplied to a logarithm, it can pop up as a power. So N of T equals 25e raised to the natural log of 2 raised to the t over 5. Well, now I can see the inverse property of logarithms and exponentials being used. And we're left with 25 times 2 raised to the t over 5. They are the same formula. So I do not care which one you use. Most math teachers do not care. You can accept either one. Okay, so let's do a couple of examples. These examples are problems you would see in your homework. So if you don't need any more than this, you can turn off the video and start getting on work on what you need to. Or otherwise, you can stay with me and we can do part of your homework together. Okay, I'm going to make this a little bit smaller so I have some room to write. So we have a certain species of bird that was introduced 25 years ago. Okay, biologists observed that the population doubles every 10 years, and now the population is 13,000. Okay, so we're trying to figure out what was the initial size of the bird population. So today, t equals 25. So that's your time, it's 25. And today, there is 13,000 birds. Okay? So that's an ordered pair we have right now. Okay? We are told that the population doubles every 10 years. So you have one of two ways to approach this problem. You could approach it with a base of 2, or you can try to go with the natural logarithm, or the base of e for natural growth, for the continuous growth model. Okay? It doesn't really matter which one you use. You should be able to figure it out either way. They want to know what is the initial size of the bird population. So if you think about this, I'm going to go ahead and just use the 2 this time around. You can use the E. I'll do that on the next problem. So I can have an equation where this is my T, and I'll just call this A to stay with A equals PERT. I can go with 13,000 equals that initial population, which we are looking for. And then this is going to be times 2 to the time, which is 25, divided by the time it takes to double. So if you want to get P by itself, that is 13,000 divided by 2 to the, and 25 divided by 10 is what, 2.5? By the way, this number, since this population is growing, this value should be smaller than 13,000. Make sure you have some reasonableness going with your answers. So let me go ahead and find that value. Fraction key is alpha y equals number 1. So the initial population was approximately 2,298. Okay, I'm just going to truncate because we can't have partial birds. So that's approximately the value we need. If you wanted to, there's another way you could have done this with PERT. For those who like PERT, you could have used the rate is the natural log of 2 over 10, because it doubles every 10 years. So then your formula would have been A, which is 13,000, P, which we're looking for, E raised to the natural log of 2 over 10 times 25 years. Okay. And if you would go solve, if you don't want to think very hard and try to do anything by hand, if you would just go solve this equation, or solve this equation for P, you would divide by E to the, let's see, 25 divided by 10, just to make it easier to type, 2.5 natural log of 2. If you pop that power up there, those cancel out. You can see it's the same thing. But for those of you not believing me, I'll show you with the calculator. I can use the divide. And you get the exact same answer. So your choice, base of 2 or base of E. Base of E, one formula for everything. Okay, now it says estimate the bird population 5 years from now. I'm going to go ahead and stay with the base of 2, this problem. So what I'm going to do is I'm going to rewrite this statement right here, except for I'm going to use T instead of 25, A instead of 13,000, and I'm going to use this number in for my P. Okay? So for part B, we have A equals 2,298 times 2 raised to the T over 10. There's my formula. Well, they said 5 years from now. Well, right now is 25 years, so 5 years from now would be 30 years. Oh, so it's going to be what? 2 cubed, 8 times bigger than what we started with. Okay, so 18,384. If you go look at a solution key, it might not be the exact value. They said estimate, so as long as they're relatively close, we're good. Something I should know for sure, it should be more birds than what we have right now, so it should be more than 13,000 birds. This seems reasonable. Okay. I also know it should be less than 26,000 birds, because if I would take 10 years from now, we would double, going to 26,000. So this number here is between what we have now and 2 times, because the number of years is between 0 and 10. So it seems like a very reasonable answer. All right, the last one says sketch the graph. Okay. We can't have negative birds or negative time. So when choosing what type of grid to make, I'm going to pick something in quadrant 1. I'm not going to label these because we're talking about things in the thousands. Okay. So we started off, let me make each mark 1,000 for the Y. Okay, so each mark here is 1,000. So we started off with just under or just over 2,200, about a little bit under 2.5 here. Okay. And then so in 10 years, we can go and try to estimate and double this value to about close to 4,600. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you go to 46 and you can plot some points. I think to make life a little bit easier, I'm going to make every one of these, let's just say 5 to start with. So 5, 10, 15, 20, 25. And the reason why I'm going to go this way is because at 25, we have a nice clean point at 13,000. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. If you want to go and put in 10 and double this, so 2, 4,600, and as best as you can, draw your function. There's different ways you can scale this. As long as you clearly mark your scaling, we're okay. So let's do number 8 from the book. Very similar to one of the ones you're going to have to do for your homework. Okay. So in this problem, we're given a relative growth rate. But in the presence of an antibiotic, then we're given the new growth rate. The initial amount of bacteria is 22. They want us to project the population after 24 hours. Now the growth rate, as we can see in here, says per hour, which means our time must be in hours, so we don't have to convert this 24 into 1 day or anything like that. So they just want us to find 2 rates. So with no antibiotic present, so the relative growth rate is 12. Okay, so we're going to project how many bacteria there are going to be in 24 hours. So I know the initial amount is 22. There's P. The other thing I need to find is R. So R is 0.12. So they've given that rate to me. If they give you a rate, then you definitely want to use perf. So we're just going to use A, or if you'd rather, N of T, if you want to make it a function notation, 22 E to our rate times our time. And they've told us our time, which is 24. Okay, the next one they want us to do is find a rate of 5%. Be careful, a lot of people will do 50%. So do 5%. And the amount is A equals 22. E to the 0.05 times 24. There should be less bacteria in part B than there is part A. Okay, so I'm just going to type this in my calculator. And I'm just going to replay it and change my growth rate. So for part A, there'd be about 391 bacteria. Normally, I just truncate when it comes to living items, like a bacteria is. You can round it, but just truncating is probably the best way to go with it. It means we're about to split off. One more bacteria is just about to double and is breaking and split into 2 right before or right after we hit 24 hours. So we'll just truncate it. That was pretty quick and easy. All right, the next one is about a frog population. They give us a nice clean ordered pair of 2 years. These are in years, time. And the population is over here, okay? So we said that some bullfrogs were introduced in a small pond. The graph illustrates what's going on after a few years. And they say, assume that it's growing exponentially. So first thing they ask, what's the initial population of the bullfrogs? Well, right there, it looks like 0, 100. So 100 bullfrogs, what we're starting with. This is find a function that models the bullfrog population T years since the bullfrogs were put in a pond. They're not giving me any double time, so I'm not going to use a base of 2. I'm going to go with A equals PERT as my basic formula. This is a more powerful formula than anything. And so I'm going to find this rate, I'm going to go ahead and put my 100 in for P. I'm going to put the 225 in for A and the 2 in for the T. That leaves me one last thing to solve for, and then I should be able to go get my rate pretty quickly. So we're going to go the 225 bullfrogs starting from 100, and we're raising the E to the R times 2. So in 2 years, we're getting what? 2.25 times bigger. So there's the ratio. If I divide by 100, I get 2.25. Then to get rid of the exponential, I convert this to a logarithm. And I'm telling you, if you can see the ratio right off the bat, you can start right here. And that equals the number of years times the rate. So our rate is the natural log of 2.25 over 2. So now we're going to find our function. And they said to use T for your years. They didn't tell us how to name it, so I can keep naming it A if I want to. So our initial continuous growth, our rate, times T. So there is our formula for part B. This is what is the projected bullfrog population after 15 years. So I can just put in my 15 and use my calculator. Make sure you close the parentheses for the logarithm. Order of operations matter. So after 15 years, we're estimating there are 43,789 bullfrogs. And then part D. Estimate how long it will take the population to reach 75,000. So that is A, and we're going to look for T, the time. So you can solve the equation dividing by 100. Or we're trying to figure out how much time does it take for it to get 750 times bigger. So if I saw that and recognized that and started thinking that way, I would just do the natural log of 75 or 750 and divide by my rate, and I'd be done with the problem. But if you want to go and solve the equation, you can go do that every single time. So I'm getting 2 times the natural log of 750 over the natural log of 2.25. And we'll just go 3 decimal places, and our unit of measure for time is still years. $15 years got us to 43,000. So if this isn't bigger than 53, I'm a little worried. It is bigger, so we should be good. So we'll take 16.327 years. Think about the original problem. It's taking, what, 2 years to go more than 2 times its size. So it would take less than 2 years to double. Going from 43,000 something to 75,000, that's less than doubling it. It has to be less than 2 years apart. So going from 15 to 16 point something is less than 2 years. It's reasonable. Okay. We're going to go ahead and skip this page. If we were doing a normal classroom setting, we'd probably go take a look at this. If you want to go play with it, you can. But we've gone through enough. You should be able to do your homework. So for today, you should be able to do problems 2, 6, 9, and 14. The 3 examples should definitely help you with some of those problems. Tomorrow, we will do decay and Newton's law of cooling. Then the next day, you'll work on a worksheet. Okay? All right.